Okay, so if two events are not independent, now be careful of the not, then the probability that A given B is the same as just the probability of B, which would be false anyway, because it would be the probability of A if they were independent. So if two events are independent, it's really the probability of A given B, but it would be the probability of A, meaning B has no effect on it if it's an independent event. The only problem you have is if it's a dependent event, and then it affects the one you're doing. The line means given. So the probability of A given B. Did this say A in your book? Probably. Did I write it down wrong? No, it did. It had it backwards. So what you're saying is this. The probability that A occurs given B occurred. If they are independent, then this has no bearing on this. Then it is just whatever the probability of A is. If they are dependent events, then this is going to make this change. It's going to change A. It's going to have an effect, such as pulling out a card and not replacing it. Then this is going to change mine. So then these is not, it's not equal to the probability of A, because A is dependent on something else happening. Okay. And really, they wrote the whole thing wrong in here anyway. This can't be right. Okay, 6. If A and B are dependent, then the probability of A and B is the probability of A times the probability of B. Okay, they should have written it as a given. Okay, they should have if they're independent, that is true. If they're dependent, then there's the given part there. So you could write that one either way. You could give me either this or you could give me the given part for that. Okay. How'd you do on this chart? The chart is always tricky, but the chart is a great example for this. Okay. The probability that a randomly selected student is a male, given that the student is a nursing major. So we're going to go to the nursing majors, because this is the given. This is what I need first. The probability that I have a male given a nursing major. This is the one I want to look at. I can't go outside of that little circle.
So I feel like the given is like the total of the given, and then for the last one, it's the amount of that number under the column of the given.
Yes, exactly.
Okay.
Exactly. Because that puts us in the total. Because otherwise I say, what is the probability that I have a male? Look at this chart. What is the probability that I surveyed a male?
Out of the whole thing.
Out of the whole thing, regardless of what kind of majors they were.
94,
How many totals are my males? It would be 1198 out of 3605 if I had just a male. Okay? Now, I want the probability that I got a male, given I have a nursing major. So all I want to do is stay within my nursing majors. So now, my probability is 94 out of 819. If these are not the same, this and this, that means something affected this total. My given did. The fact that I said, don't look at the total, look at just the nursing majors. That means this is a dependent event. I'm dependent on what part you tell me. I said, look at the nursing majors, not the whole thing altogether. So do you see the difference when we talk dependent and independent? Anybody not see this difference? This is really important that you could read it off this chart. Okay? So next question. The probability that a random selected student is a nursing major, given that the student is a male. These are two different things, because my given is the one that comes here. So given that I am a male, I'm going to be in this whole row. And I'm going to use this total. So given that I am a nursing major, 94 out of this. What is the probability that I am a nursing major for the whole chart? Good. So are those the exact same totals that we got? They're different, right? Meaning something had to affect that if it's different. That's what my given does. And I like the chart because sometimes when we say these two things are independent or these two things are dependent, you say, well, what's the difference? Kind of when you use the chart, you can see it. Because the probability of a male should have been regular. The probability of a nursing student should have been just what the nursing student was, unless something else changed it. It had an effect on it. And what has an effect is my given. Good? Okay. All right. Now, last one. The probability that a random selected student is a nursing major and a male. So what is it I'm looking for? A nursing major and what? A male. 94 out of what? 3605. I'm not in any column now, but I need them to be happening at the same time. I need this person to be a male and a nursing major. It just so happens they intersect right here, but I have to go based on my total because I kind of combined everything with this. So only 94 of those people that out of 3,605 were actually a male nursing major. You could rewrite this. A male nursing major. Does that make more sense if we just say, how many male nursing majors do we have? That's what an and statement does. It has to happen at the same time. So if I want a female nursing major, I want the probability that it is a female and a nursing major. I want this one out of my total. You kind of seeing how this chart works? The chart, I like the chart because I think it explains things a little easier. But I know some of you guys struggle with the charts. So unless you talk to me, I'm assuming that it's good. Okay. The probability that 1 month or more income was set aside for emergency. I have less than 1 month's income set aside, 1 month's income or more set aside. Okay? The probability that 1 month or more income was set aside for emergency. Do I have any other things that are contingent on this? Just that, right? So I find, where am I 1 month or more? In this row, out of this total. I didn't say given a male, given a female. Okay, there was no given here. Was that on your sheet or did I add it there? I might have added it there. Because sometimes we do all these givens, but you don't take it right off your charts to begin with. Okay, so let's take a look at the rest of these. The probability that a randomly selected worker has 1 month's income or more set aside for emergencies, given that that worker is a female. So what row or column am I going to look at? Woman. I can't go out of this row, out of this column. So then I find has 1 month or more, so 62 out of 145. And either reduce it in lowest terms fraction, which your calculator will do for you. Just put in 65 divided by 145, flip it back to a fraction. Or, easier, give me 3 decimals. I like the 3 decimals only because watch what happens when you're looking at these. These are all different denominators. So when you're comparing which one has a better probability, it's a little difficult to compare two fractions that have different denominators. If you go all to decimals, then you can say, well, yeah, 0.557 is slightly higher than 0.428. So this one had the better probability of happening. So probabilities, 3 decimal places. probability that a randomly selected worker is a female given that the worker has less than 1 month's income set aside. So where's my given? A row or a column? A row. Less than 1 month's income set aside. And I want that it is a female. Female over total. Good? Will you have your work?
Yeah.
Okay. Probability. Now, this one they switched around, so be careful with this one. Okay, they switched this around here. So they said, given that the worker is a male, find the probability that the worker has 1 month or less income. So the given came first, which is perfectly fine. But you still have to do the given first. So given the male, find the probability that it has less than 1 month, 66 out of 142. Good? Okay, what is the probability that I have a male and he keeps 1 month's income or more? 1 or more income. 1 month's more income. 76 over 287. 287 because it has no given here. This is the and situation. My and situation says a male, he has to be a male, and he has to be this. But I'm not in this row anymore. This is the only thing that they intersect over my total. Okay. Yes. Then it would be the total of the you find in your given. But you can write it a little differently. So it depends how they write these things. You really got to watch the wording on these. Okay, selecting the king from a standard deck of 52 cards, replacing it, and then selecting a queen from the deck. So they wanted to know, was this independent or dependent? When it says with replacement, that means you're putting it back in, your total is not going to change. Your king, 4 out of 52. Your queen, 4 out of 52. This is an independent event. Good? Okay, a father having hazel eyes and a daughter having hazel eyes. Would this be a dependent or an independent? It's a dependent. And this is one of those subjective dependents, or you can make that little chart like they did with the snapdragons to see what the probability of having the same eyes. That's a trait that's passed down. So it has some dependency. Does that mean that the daughter is going to have hazel eyes? No. It could mean that the daughter takes the eyes of the mother, or the daughter has the eyes of neither the mother nor the father, depending on the way it rolled. Rolling a six-sided die and then rolling a die a second time so that the sum of the two rolls is 5. Does one roll of the die have any effect on the other roll of the die?
No.
So what is the probability of getting a 5 on the first roll? What is the probability of getting a 5 on the second roll? And the third roll? It won't change. It has no effect. We can't remove it off the die. Okay, so that is a... Oh, what does this say?
Because if you're doing the sum, don't you have to do both going in?
Sum. Oh, I'm sorry, the sum. Oh, the sum. That's what I totally missed, was the sum. Yes. Sorry about that. I missed the sum. Yes. The sum changes it, makes it a dependent event. You want to know an easy way to do the sum of your die? This is an easy way to do the sum of your die. You have 2 dice. 2 die. Yeah. Your 2 die, you roll together, so you take the sum. There's a pattern. This goes 2, 3, 4, 5, 6, 7. This goes 3, 4, 5, 6, 7, 8. 4. I'm just taking the sum. So a 2 and a 1 is a 3. A 3 and a 2 is a 5. See it? There's a pattern. Anybody that knows anything about rolling dice? 11. The 7, when they ask for a 7 or an 11, the 7, the sum of 7 occurs the most. It's on the diagonal. So when they ask for this, a 7 or 11, the 7 does occur the most. The 11 occurs twice. So out of 6 times 6, out of 36 possibilities, you have the diagonal, which is 6, 7, 8. You have 8 possibilities to get your 7 or 11. You know, you hear those games, 7 or 11? Or get a snake eyes. A snake eyes only happens once. Okay, and that usually, I think, like ends your roll or whatever it is. But these are where they get your probabilities from. The sum of the dice. Okay. A study found that people who suffer from moderate to severe sleep apnea, that should be apnea, are at a risk, not area, an increased risk of having high blood pressure. Identify the two events and state if they are independent or dependent of each other. Now, you have to have two things that happen. Event 1, having moderate to severe apnea. Event 2, what's the other thing that they're checking on? High blood pressure. Event 2. So would you find that that is dependent or independent? Dependent. And what gave it away in the words?
What is the relationship between them?
There's a relationship between them. You have an increased risk if you have this. So that gives you that dependency. It's dependent on that. Are there other factors? Yes. But the fact that if you have moderate to severe sleep apnea, it raises your chance of having high blood pressure. So they're looking for you to separate it into two things that are happening, two events, and then to state if they're possible to be related. A study found that there is no relationship between being around cell phones and developing cancer. So the first part, being around cell phones. The second part, developing cancer. According to this survey, this study, are they dependent or independent?
Independent.
Independent. Why? What does the study say? There's no relationship. There is no relationship between this. So if there's no relationship, then they're independent of each other. Now, that's one of the things that I find when you take a statistics course and you read these things, sometimes you question them, and you should. When did they do this? How long was their study? Like, cell phones haven't been around that long compared to everything else. And sometimes it takes years and years before they realize that there's a problem. So always look to see, is it possible to find out anything more about this study so that you can make that conclusion yourself or look into it. 1 in 400 women carry a mutation of the BRCA gene. 6 out of 10 women with this gene will develop breast cancer. So what is the probability that you carry the gene and you develop breast cancer? So the and is where we multiply. So we take these two pieces and we multiply them. Okay? So even with that, it's a small chance. And we keep it to your significant digits. Now the reason they went 4 on this is watch. Because if you go here, you're just saying 0.1%, so they went a little bit further on that because they kind of got rid of everything in the front of it. So they just went with 0.15. You want to keep it 3 decimals, that's fine with me. We're not doing anything beyond just getting concepts and things like that. And I'm sure in the real world, they would bring those out a whole lot more. But you have a hard time telling people, well, you have a like 5% chance rather than less than a 1%. You probably would say less than 1% chance to people. Okay? Are we doing okay so far? You guys have no questions? In a sample of 1,000 adults, 180 dine out at a restaurant more than once per week.
Can we make the screen bigger?
Yeah. Better?
Yeah.
Sometimes, yeah, it's a little dark. Maybe I use a lighter ink on this one, too. Okay, find the probability. You select 2 adults at random without replacement. If I say without replacement, are these going to be dependent or independent? Without replacement, dependent. I'm not putting that one back into the mix. These are dependent. So find the probability that both adults dine out more than once a week. Now I've surveyed 1,000. If I surveyed you guys and I asked one person, I'd keep you over here. And then I'd have to survey the rest. So the bottom number is going to change. That's what makes it dependent. Find the probability that both. So adult 1, adult 2. So the first one, 180 dine out more than once a week out of 1,000. I keep that person. Now I have 179 left out of 999. And I multiply those. That's my dependent. If this was independent, then I would have, if I put them back in the mix, but the chances are of me pulling out the same person might be slight, but still could happen. And I certainly don't want to pull out the same person. Do you see why they don't ask that person again? You need to ask 2 people. So they said if you already asked this person, however small probability that you could snag the same person again, we don't want this to happen. Find the probability that neither adult dines out more than once a week. Use your complement case. Out of 1,000, if 180 dine out, then 820 do not dine out. God bless you. Use your complement case. So again, it's dependent, because we don't want to take a chance that we're going to take that same person back out. So we get 820 out of 1,000 times 819 out of 999. And there would be a better probability than the not part, right? Because there's more people to choose from. It would make sense. Find the probability that at least 2 dine out more than once per week. The only one you don't want is that neither dines out. So use your complement case. Okay. And they want to know, do you consider this unusual? And again, this ties back into your normal curve. Your normal curve says plus or minus 2 is 95%. So if anything is to the right or to the left of your curve, this is your plus or minus 2. So this and this add up to 5%. This adds up to 2.5%, 2.5%. So if I find something less than 2.5% or more than 97.5%, then I've got something unusual. So both of these were less than even gauge, but less than 5% or less than 2.5%, then you're fine. Okay?
Yeah.
Just this guy. Just the first one. These guys were okay. This guy was under. Well, I guess they consider 5%, so if you want to say that that's close, or that one's pretty unusual. That one would be the more unusual one because your number is low out of 1,000 people, 180. But when you take a higher number, it won't be as unusual because now you have the majority of your people answering yes to your question.
So for the at least word, how do you know it's going to be?
The at least, the only way we can do it right now before we make a chart, we're going to be making a binomial distribution chart in the next unit. But right now, the only thing that we're going to do now is use its complement case. So we're going to say, if it's at least 1 or 2 adults dine out more than once a week, I don't want anything that doesn't dine out at all. I don't want the case where they don't dine out at all, which is the one where they didn't dine out over here. We did this one. So I want to just subtract it. I can take one adult dining out. I can take two adults dining out. I just can't have no adults dining out. I think this was a little harder to see with the adults dining out. I think the one we did in the regular class was a little bit easier to get. Because this one is a little tougher to get. Just the case. Sometimes the case alone is a little harder. Not the concept, but the case. Okay. In a sample of 2016 U.S. adults, now that's the number, 2016, not the year. So the number 2016 U.S. adults, 383 said Franklin Roosevelt was the best president since World War II. Two adults are selected at random, again, without replacement. That means if we ask somebody and they responded, we don't want to ask them again. So we're just keeping them out of the mix, which is kind of a difficult thing when you're asking that many people in the room. They probably ask and then randomly pick another and pull them out. So this is kind of like the last one. This is a dependent events. So your total is 2016. If 383 said yes, then the 1 minus take away 1 would be 282. Kind of like almost the exact as the one before this. Find the probability that neither says yes. You have to use the 2016 minus 383. This says neither says yes. So if you're looking for the at least one, the only case you don't want is the neither case. Shayla?
For 25, it says 2 US adults. How can you subtract the 1
We subtracted 1 because they're asking without replacement. They're selecting a person from this group, and they said was the probability that this person said yes to their question. Rather than put them back into the group, they kept them over here. Yeah, and then they did it a second time. That's this. So the first adult to say yes, adult 1, adult 2. So when it's an and condition, we multiply. And they said, did you consider this unusual? And both said A was the small one again. This is almost the same exact as the one before this. Hopefully you're getting this and not just totally bored. Okay. This was a nice one. I love when they give you the ones where you have to lay out the lines. The probability that, excuse me, that a person in the U.S. has B positive blood is 9%. 9% we write as 0.09. Move your decimal place 2 places. 5 unrelated people in the United States are selected at random. You didn't want them related because their chances of having the same blood type will increase if they're related, won't they? So you really wanted to keep this random. So there's where your 5 unrelated people came from. Find the probability that all 5 have blood type B positive. Lay out your 5 lines. First of all, is this an independent event or a dependent event? Independent. Because once I select one, am I putting this back in the mix? No, I'm just keeping selecting people and my probability of B positives will not change. Find the probability that none had B. Use your complement case. If 0.09 is that they had B, 0.91% or 91% didn't have B positive blood. Find the probability that at least one, all you don't want is the one that had none, which was this guy. There's your complement case. So do you see us using the complement case with a dependent versus and an independent? We're still using your complement case. In chapter 4, we're going to make binomial distributions. And we'll make the whole table, and you can add them up off the table or use the complement case. And all 5 these are pretty rare to get you all 5 because that's a very small percentage to have be positive. Did you ever, like in science, do the write-up about how popular the blood types are? In biology? No? You did they usually do those things. And they, God bless you, and they tell you if you, O positive? Yeah, one's a universal, one's the most popular.
Oh, it's universal.
Oh, it's universal, yeah. But they usually do like a write-up, like they'll ask your parents' blood type, your blood, and your parents to see where your blood type fits in. What are the chances? What I'm not really sure is how like the RH factor comes into play. I'm not sure about how that one comes into play because that's very rare in itself that you get a negative. Okay, now I threw this one at you. Do we have to memorize this? No. But you should have been able to take what was there and just substitute it into the formula, right? So all I wanted you to do was substitute it in. Bayes' theorem, it's just a probability theorem, and all I needed you to do was to either put it in with fractions or put it in with decimals, so that you can kind of just see how it works. We don't use this. You won't be tested on it. It's just a good exercise with your calculator. Yes. Okay, I'll give you a deck of cards.